Good morning, students. Let me start the class. We are discussing about transformation of electric and magnetic fields under Lorentz transformation. Now, since we know that electric field and magnetic field are components of the second rank tensor, either it is covariant or contravariant. We are taking the contravariant field tensor. Now, we wish to transform it in another inertial frame is moving with velocity u with respect to the stationary observer. Now, transformation rule for second rank tensor is like this. Suppose f dash ij, this is the transformation matrix tensor in prime coordinate. This will be equal to, since we are doing Lorentz transformation, f I l I k l j l f, right? Now, transformation of these fields, we know Lorentz Lik is of the form Lik. It is a symmetric tensor. So if you it is same if you change the indices gamma 0 0 minus gamma beta 0 1 0 0 0 0 1 0 minus gamma beta 0 0 gamma. So this is the Lorentz transformation matrix. Lorentz matrix. Now, using this relation, we can find the relation between the different components of electric field and magnetic field, between the prime coordinate and unprime coordinate. That means between the quantities in moving frame with the quantities in rest. Now there are two ways to perform this thing. First way is very simple, straightforward. You calculate component wise. For example, I am taking f dash 1 2. 1 1 will be equals to 0, as you can see, because it is 0. It is asymmetric, antisymmetric. So f dash 1 2 equals to here 1 k l l f k. Now since k and l are repeated index, so this implies summation. So we are taking over the summation. First summation over k, the summation over l. Now if you look at the matrix, Lorentz transformation matrix, you will see that only few terms are there. Say L11 is there, and for L2 only one term is there. L22 is there. It will be F12 plus L14 is there. So L14, L22 is only there. So F42, right? These are the two terms. Now reading out these two terms, L11 gamma, L22 equals to 1, F12 plus L14 minus gamma beta. So I am putting here minus gamma beta. L22 1, L22 is 1, F4. So now reading out the term F12 contravariant tensor Now F12 was minus CBZ. So gamma CBZ minus CBZ minus F42 was minus EX, sorry, minus EY. So minus gamma beta EY. So it will be minus gamma CBZ, I'm sorry, gamma beta minus here this will be plus, EY will be minus 42 plus gamma beta EY. Right. Now, since F dash is the contravariant field tensor in the transform coordinate, it must be minus C D Z dash. Right. So if we compare this thing, take a minus gamma C common, this will be dz minus gamma is taken beta by c ey. So straight away you can find the relation dz dash will be equals to dz minus beta by c ey. So this is the relation between transformed coordinates and magnetic field in the z direction. The moving frame is equal to the magnetic field in the rest frame minus beta by c ey. So electric y component of electric field is coming into the magnetic field. Similarly, you can calculate other terms also. For example, I am taking another example. Suppose I am now taking f dash 3 2, f dash 3 2. So this will be L 3K L 2L Fk. Now again summing out this term scale. For 3 only one term is there, L3. For 2 only one term is there, L2. So here only one term is there, right? You see, only one term is there. So this will be equals to straightforward. This is one, F3. So F dash 32 will be equal to F3. Now reading out, what is F32? F32 was nothing but CBX, and this will be CBX dash. So straightforward we can see that Bx dash equals to Bx. That means X component is not changing. Similarly, other components you can find. And there is a second method. You already know, you have done it. The second method is do the matrix multiplication of these three matrices, giving due respect of the to the matrix multiplication. So this will be written as, if you use matrix multiplication method, that this will be Fik Fal, and this will go this side, so it will be transposed F L F J. Sorry, this will be K, this will be J, this will be M. Right? Taking transpose will not alter this thing j. So now you can multiply this. So there will be three matrices. If you can perform the matrix multiplication, I am giving it as an exercise for you. Please perform the matrix multiplication. Then you will see that the transform matrix will be something like this. Zero minus gamma c dz minus beta y c dy. It will be the second component. Third component will be gamma c by plus beta y c z. Fourth component will be dx. Then it will be its reverse component gamma y c dz minus beta y c dy. This will be 0. This will be gamma c minus. This will be minus cdx. This will be minus cdx, and this will be gamma e y minus beta c dz. This component will be minus gamma c dy plus beta y c z. This will be cdx. This will be 0, and this will be gamma ez plus beta c dy. This component will be minus x. This will be gamma y minus beta c dz. This component will be just minus gamma ez plus beta c dy. Beta c dy. And this will be 0. So this will be the transform matrix. Once we perform the operation, you see this is negative of this. This is also negative of this. This is also negative of this. These are also negative of this thing. You see. So maybe there may be some mistakes. Please check it, see whether this transformation is, this matrix is right or wrong. Then reading out these things, these elements. So transform coordinate, this will be minus cbz dash, this will be c dy, this will be dx, right? This term will be ey dash, dx dash, this will be ez dash. So the transform quantities will be ex dash equals to dx, ey dash equals to gamma ey minus d dz, ez dash equals to gamma ez plus dby, and similarly dx dash equals to dx, dy dash equals to gamma dz plus beta by c ey. Beta by c, I'm sorry, dy equals to b, this will be ez, and dz dash will be equals to gamma dz dash minus beta by c ey. So these are the transform quantities, electric and magnetic field transform quantities under Lorentz transformation. Now there is another approach method. I have mentioned it in the first class. If you follow Griffiths and other books, they have not gone to this four vector formulations. Four vector formulations is there in Jackson and some books, few of the books, textbooks. In Griffiths, you can see that the transformation relation has been derived using the Lorentz transformation rules, but the treatment is somewhat very different. The logic has been used, but all these things were made to fit this transformation rule. These are correct. So these are the transformation rules. So using four variant formulations, once we have realized that electric field and magnetic field are basically component of a field tensor of rank 2, either it is covariant or contravariant. Now we know the rule of transformation of the tensor of rank 2, and we use that rule to find the field tensor in the transform coordinate. As you can transform the coordinates to four vector under Lorentz transformation, you can also transform electric field, electric scalar and vector potential, and current density, charge densities. This can also be transformed. So up to this, the covariant formulation of mechanics is nearly complete. Only one point is there, which is very important, which is important in the sense that when you will in the next semester, when you will study quantum mechanics, and in fourth semester when you study particle physics, field theory, then you need to understand that the Lagrangian formulation for the particle physics is also applicable for the electromagnetic fields. Now, I am trying to give you the basic equation that governs the electromagnetic field, which can be treated using the Lagrangian formulation is the Lorentz force equation. Now, I am going to discuss about covariant form of Lorentz transformation. We have finished the covariant formulation of electric field, magnetic field, scalar potential, vector potential, charge densities, and current densities. Now we will extend, and this will be the last step forward, step for the covariant formulation of electrodynamics. Now we will discuss covariant form of Lorentz force equation. Now we know Lorentz force equation is F equals to dPdt equals to Q E plus U cross B, where U is the velocity of the particle, charged particle. Now, since we have derived electric field and magnetic field in such a way that electric field is E and magnetic field is CB. So we are just modifying the equation Q by C EC C into E plus U cross of CB, right? So that we can write E and CB to be the part of field density, components of field density. So these are basically three equations. We can write it in component form, but we are coming it later. There is another equation in if a charged particle is moving in an electromagnetic field, then there is another equation which is called energy equation. Energy. What is this? That is energy dissipated in an electromagnetic field. You know, magnetic field does not do any work on any charge because the charge is moving perpendicular to the magnetic field direction. Only work done is for electric field. So energy equation equals to Q into E into X. This will be energy equation. Sorry, work done. Now energy equation is say energy is here we have used E, so I am using S. Energy equation rate of work done ds dt will be equals to Q U dot of E. Right? This will be the energy. So Q into E is the force, and if you multiply it dot product with X dot, it will be the work done, and we are taking rate of work done. So it will be Q dot of E. So these are the two defining equations which we will consider. Why this equation has been introduced, it will be clear at once. Now we are just considering four velocities. Four vectors. So we have defined four velocities. Four velocity vector has been defined. So we have to use four velocity vector because velocity vector U is there, velocity vector U is there. We have to use four velocity, and ultimately there is momentum. So we will go to four momentum formulation. So for velocity U alpha has been defined dx alpha by d tau, right? Where d tau is the proper term. Now we know d tau equals to dx alpha equals by dt and dt by gamma. So one gamma will be there, right? And x alpha equals to, we know, gamma ddt of, we know, this is r ct, right? This is our coordinate. So if you work it out, so this will be gamma. This is u, nothing, and this will be c, right? So for velocity u alpha equal to gamma u c. So consequently, four momentum. What will be the four momentum? Four momentum p alpha, by using p alpha equals to m0 u alpha equals to gamma m0 u m0 c, right? So if we gamma m0 equal to m, so m equals to p, so this will be p, right? 3p momentum, and gamma m0 equals to m, so mc square equal to e, that means s by c. Okay, gamma m0 is m, and mc square equals to total energy. We have used total energy. S equals to total energy. So substitute S as energy. So four momentum is P and S by C, where S is the total energy. Now, once we have formulated this thing and this thing, now we are going to represent this equation, Lorentz force equation, into the form. For example, if I take first equation, I am taking say the first equation, first component. Then say first component will be equals to say dp1 dt, right? Now since dt is not proper term, d tau is proper term, so therefore we are using dp1 d tau. What we have to do, we know from this relation, we know d tau equals to dt by gamma. So we are using d tau in terms of dt, so dt equals to gamma d tau. There will be a gamma, so one gamma will come here, right? Gamma q by c dp1 dt, and this term will be equal to c ex, right? c ex, and this will be equals to first term. So u cross of cv, the first term will get uy cvz. So this will be, I am taking advantage of the board, uy cvz minus it will be uz cvy, right? So dp1 d tau will be this thing. Now this is equals to q by c. This is gamma c ex plus gamma is introduced here. This is equal to gamma uy cvz. This is equals to gamma uz cvy. Now we see that one is component of, this is fourth component of velocity, for velocity. This is second component of velocity. This is third component of velocity, and ex is field tensor. Now, if I represent it as contravariant field tensor, then ex is nothing but f14. So we can write this equation q by c as ex is f14 and uc is u4, right? And cvz will be equals to f cvz what to 1. I'm writing f12, f12, so minus sign will be there, and one minus sign will be absorbed here because we are writing uz in, so this is equals to u2. Okay, this u2 will be negative. See, f12 is negative, so double negative positive. Here plus cby. cby is f13, and this is u3, right? Minus sign is there here, right? You see the pattern 144 122 133. There is one term missing, you can easily put it 111. So this can be written as q by c f 1 alpha u alpha, right? So first term is there, dp1 d tau is this. Now you can easily write out the other terms. Other terms dp2 d tau will be equals to q by c f 2 alpha u alpha, and dp3 by d tau will be equals to q by c f 3 alpha u alpha, right? So 1, 2, 3 is complete. Now we have to look for fourth component. Now you know fourth component of p alpha, we know p is by c, right? The fourth component of momentum is S by C. For that we have to look for energy equation. And the energy equation, you know, in an energy equation was, so if we write similarly dp4 by d tau, this will be equals to basically, so since four terms is S by C, so 1 by C ds by d tau, right? Now ds by dt was there in energy equation, so ds by d tau will be equals to q by c gamma u dot of e. So gamma ux ex plus gamma uy ey plus gamma uz ez, right? So reading out these terms, gamma ux is first component of velocity, and ex is 1 2, ex is sorry 4, ex is 1 4. So this reads out to be q by c f 1 4 u1. Sorry, I'm sorry. It will be f41. I'm sorry, it will be f41 because double negative will imply positive. u1 plus f42 u2 plus f43 u3, right? So this will be, in fact, this can be written as q by c f4 alpha, sorry, f4 alpha e1. So it is in the same line. So now we can write these equations in this form, that dp beta d tau equals to q by c f d tau alpha q. We can write this equation. So basically this is the force equation. This is the force equation, Lorentz force equation in covariant form, right? We have for beta equals to 1 2 3 4, beta equals to 1 2 3 4. For d beta equals to 1 2 3, we get the Lorentz force equation, and for beta equals to 4, we get the energy equation. These four equations constitute the covariant formulation of Lorentz force equation. Now in the next class, I think it will be very tough, difficult for you to grasp the next formulation, which is basically Lagrangian Hamiltonian formulation that I have told you. For that thing, you have to memorize the classical mechanics that you have read in your UG classes. So I will discuss it in the next class. So for the time being, I stop here with this comments that the Lorentz covariant form of Lorentz transformation equation can be done. You see that this is the field tensor, covariant field tensor. Now you can express this thing as gradient of something. You know if alpha beta or something like this. You will express this equation, then this will be del alpha, del beta a alpha minus del alpha a beta. This is actually the expression. So del means derivative of potential, So force, force is derivative of potential. So the derivative of potential is there, and its rate of work done, one velocity vector, velocity covariant form of there. We will discuss it in the next class, and it will be helpful, useful for your higher study, right? So today up to this. Thank you, students.